Greeting Earthlings, if you follow the channel, you know that we are resurrecting the Apollo communication system with original spacecraft and NASA ground equipment. Over the last 2 episodes, we finally hooked up one of the last pieces into this complex system. We powered on the PCM, the surprisingly powerful digital telemetry box that flooded the flight controller screens with large amounts of data. No kidding, it could transmit 365 analog signals and 304 digital ones at the then astonishing rate of 51.2 kilobits per second. And now that we finally understand how to connect it, it seems to still work perfectly fine after 50 years of slumber. However, while we were debugging it, we encountered a very strange and unusual circuit. It was the analog multiplexer. You see, since they had only one analog to digital converter in the box, or to be exact 2 for redundancy, but only one active at a time, there had to be some way to switch the 365 analog inputs to the single ADC in sequence. This analog switch is called a multiplexer. Since they had to do this really fast, a simple relay switch was out of the question. Today this would be a cinch. We'd use an analog switch integrated circuit, which does the switching internally using modern CMOS transistors. But they had no such things at the time. Enters one of the weirdest analog circuits we ever found in Apollo. It's so weird we had to build one for ourselves to convince us that it actually worked. So today we have a mic.
Hello.
And a weird circuit and a weird schematic. So we came onto that while we were wiring the PCM. Right?
Yes, yeah. So the PCM has something like 150 analog inputs that it multiplexes all together to go into a much smaller number of ADCs.
Yeah, so you should say what the PCM is, right? So that's the...
It's the telemetry box that takes in a whole bunch of analog inputs, a whole bunch of digital inputs, packs them, it does all the ADC stuff to translate all the 0 to 5 volt analog voltages into digital numbers, and then frames all of that up and sends those frames to the ground for decoding for
right,
telemetry.
and that's basically all the digital data that comes back from the ship.
Yes.
And then fills the flight controller screens, right? Comes to that device.
Yep.
It only has one A to D in there? Or maybe a couple?
Yeah, one or a couple, but certainly not 150.
A few, right?
Yeah.
And then you have hundreds of signals. So what you do, if you put a multiplexer, you switch the signal electronically to your ADC.
Exactly.
They did it a way that surprised us because it's done the 1960s way. And we were confronted with that circuit, which got us scratching our heads for a while. Our inputs are here. Mm-hmm. Our output is all on the emitter of each transistor, all coupled together. Mm-hmm. The transistors are malformed. They have 2 emitters. They are fed by core, by core flipping, core logic. And no, this is another one of those circuits that you say, no, this is fake. This doesn't work. Right. They made it up. How can that be a switch with bipolar transistor? Uh-huh. And then you discover that those transistors with 4 pins do exist. They have a name.
Yeah, they're actually also used in the coupling data unit,
which is the analog to digital unit for the Apollo guidance computer.
Yeah.
Right.
So back when I thought I was going to have to build my own CDU to try to replicate the Apollo 11 problem, I was looking into can I buy all the parts for a coupling data unit? And I found some of these. They're 3N68s. Is these 4-legged transistors.
We confirm they have 4 legs?
Yeah. So I found a pile of these on Etsy, of all places, and ordered them.
The place where you buy all your Apollo components, of
yep.
course. And you even found the spec sheet.
Yeah. So Don Isles had in his collection...
so can you hold it for me so I can film it? So it's legit. I mean, this is an early device, 3N68, right?
Yep.
They hadn't invented the 3-digit devices yet. It has this weird symbol where the collector is at the wrong place and slanted the wrong way. It's called an inch.
Yep, the integrated chopper, or shortened to inch.
All right, so we still didn't believe it, so we made a circuit. You made a circuit.
Yep, so I had the inches and I had some tape-wound cores with the square hysteresis loops, so I built it just to see what would happen.
Ah yes, I forgot to mention, the four-legged inch is not the only strange component you need to build this weird circuit. You also need giant tip 1 magnetic cores, the same kind that were used to build the equally weird core rope memory, the permanent memory that was used to hold the Apollo guidance computer programs. I have an excellent video about that if you want to refresh your memory. In there you'll see a live demo of how the cores work by flipping their magnetic polarity. Go flip the cores!
Okay. So if we hit the set wire, you can see the core flipping in the yellow trace.
In our multiplexer, the magnetic flip is used to generate a current pulse and activate the inch switch, to make the inch switch twitch as if it were bewitched. We built two channels,
Yep.
So you have 2 inches.
Yep, so there's 2 inches
Right.
and 2 cores, one core for each inch. And then I have 3 current drivers down here, one to set the first core, one to set the second core, and then one to reset both of the cores.
You built 2 stages of this, right? So this represents a core with its windings, which is driving the transistor an incomprehensible way, right? Because it's driving it between the base transistor, the base and the collector.
Yeah, so specifically how the inch works, practically, if you're using an inch, is if you drive the base high with respect to the collector, then the 2 emitters become connected.
Together.
Which is very strange.
And yeah, the way I explained it first is that they must have made it was a 2 transistor thing at first, and they were making a voltage mirror of some kind. And what we'll see later, that's actually how it happened historically, and then after that they made a double device. But still, to bias it, they use core logic, they flip core, so let's see if it works, and then we'll try to explain it. To figure out what goes into the core, I use 2 differential probes with a little extra wire. It's my HP differential probes here. So on the yellow trace, you see 1 core flipping, then it's being reset, then flips being reset. And you see the same thing is done at a little different way on the second core. It's flipped later, and they are reset at the same time. On the cores themselves, there are 3 cores. Am I correct,
Yeah,
Mike?
3 coils on each core, 1 set coil, 1 reset coil, and 1 sense coil.
Right, and I added a fourth 1-turn wire to sense it. And then I have 2 input voltages on the emitters, and then we look at the combined output on the other emitter, and I can vary the voltage of one guy and vary the voltage on the other guy. And I'm sampling. This is not a hoax, guy. It really works, and it works incredibly well.
Yeah, remarkably well.
It's super stable. It samples my signal. There's no leakage from one channel to the other. The circuit is powered by 5 volts, but I can sample 10 volts easily. It's really a switch. So we were kind of trying to understand how it works, and we convinced ourselves that it's just connects the 2 emitters. So it should work with an AC current. So that's what we did. I hooked up my oscillator over here, working at a couple megahertz. This is super fast, by the way. We are sampling on a couple microseconds. So I'm working at 5 megahertz over here, so I'm going to take that signal off, so now it's gone from over there, and connect it to what comes from my signal generator. And here we go. The AC comes right through. A is connected to B during the period of the core flip. You can see core flip right here. So boom, single. So right now I have a triangle wave. I'm going to switch it to a sine wave. Sine wave. It's DC couple. I can move it up, down. I can get negative. It doesn't matter. The 2 emitters of my transistor are magically connected.
Yeah, either magically connected or completely disconnected.
Oh, completely disconnected. What a circuit. And then what happened? J effect happened and then they ignored this? Or?
Yeah, well, I mean, it's really an awkward kind of thing because you have to make the base high with respect to the collector, but as your emitter, your input emitter voltage moves around, the voltage at your base collector junction is going to also move around. So in order to actually drive the base and collector apart, you have to use something like a transformer
You have
or
to
a
use
magnetic
magnetics,
core.
right? So you have to float everything.
Right.
And then we went to the patent of the original inventor. And no, I was wondering, why did they invent it with a single transistor instead of taking two? And why did they bias it between the collector and the base instead of the emitter and the base, like anybody that's sane would do? But it turns out the inventor did exactly that. And it is exactly what I thought it would. They did a voltage mirror. And they do turn it on between the base and the emitter, like any reasonable person would do.
Right.
And what happens is in saturation, so they drive it really hard. So the voltage over here is Vsat, which is pretty low. Here's another Vsat. So you get plus Vsat minus Vsat. Right? You go up, you go down, and the voltage that you have here happens to be there, right. Basically. With the problem that you have to float the whole biasing section.
Right, yeah.
Because it has to move to the same level of your source. And then I saw the second picture and say, aha, that's how the Apollo guys implemented it. They biased it between the base and the collector. And then we went into the description of the patent. Why do you do that? And
they don't know.
They don't know. So if you read the text of the patent, they say, well, we tried that and we understand how it works. And then somehow this one works much better.
Yeah, I think their wording was, it was discovered that, which is, I think, a way to say we accidentally plugged it in backwards one day.
I bet you this is exactly what happened.
Yeah.
Is that they were doing that, and then somebody wired it the other way around. It worked 10 times better.
Later.
So Mike, you were saying that you might have found why a transistor is better when it's wired backwards on the circuit?
Yeah, I found something on the internet that said that the saturation voltage between the emitter and collector is much smaller when you use a transistor in reverse instead of forward like normal.
And also we're going to test if the internet tells us the truth. So we took a 2N23904 regular transistor, wired the right way. And it's an excellent transistor, and actually the saturation voltage is at the knee of this curve, right? It's the space between the vertical of that point and over here. So it's like 250 millivolts, pretty good. All right, so now we'll use the transistor backwards. We'll invert the emitter and the collector and see what it does. Doesn't work very well.
Nope, the gain is gone.
The gain is gone, so you just get to it, and then you see that indeed the curve is vertical, below 100 millivolts in Vsat,
right.
Way below that.
So the reason this would be good in this circuit is because we don't really care about the gain.
You don't want any gain, you don't need any, right?
And the VCE sat is what we're adding and subtracting. So the smaller that is, the smaller the error in it is going to be.
Yeah. But yeah, I think you found why. A reverse transistor is terrible gain, but when you don't need any gain, it has very good Vsat. It worked much better like this, and they discovered it accidentally. But I think the physics is more complicated because it's the physics of a saturated transistor. Mm-hmm. So that's the NPN. So that's the collector, the base, and the emitter. And here it has two emitters, so it's a four-legged device. So you turn the base collector junction forward. It puts the transistor in saturation. Basically, you inject a ton of carriers in the base. Mm-hmm. And then what happens is that your semiconductor that you had here is a conductor now. Mm-hmm. Then this becomes coupled to that. Whatever junction drop you take here, you take it back here exactly the same way. So the voltage here is exactly as the voltage there.
Mm-hmm. Yeah, and the spec sheet here has an offset voltage spec, which is for the 3N68 plus or minus 200 microvolts difference between the two emitters.
It's just, yeah, perfect.
Yeah.
Right? It's just the magnetics. And but it's simple. You can wire it yourself, right?
Yeah.
It's not that many turns.
Yeah, just a few turns on each coil.
So here you have it, the miracle circuit with 4-legged transistor connected backwards with core logic.
And a silly name.
And a silly name. And it works. I can't believe it, how well it works. It's just completely independent. No action of one on the other. Large dynamic range. And invented in 1950 something, right?
Yeah, the inch was, I think, early to mid 60s, but the circuit that the inch is based off of was 1954.
This Apollo thing is not a hoax. They just made circuit with what they had that were genius.
Yeah, and if it wasn't for the downfall of needing magnetics, it would be a really good way of doing this.
Yeah, we run it at a megahertz.
Right.
We are sampling at a megahertz. No problem.
Yeah.